Imagine an ultra-dense cosmic bullet, a city-sized neutron star streaking through our solar system. To the untrained eye, it's just a dark dot, but these dead star remnants carry almost unimaginable forces. Neutron stars are born when massive stars explode, leaving behind a core about 20 kilometers across with roughly 1 to 2 times the sun's mass. A teaspoon of neutron star material would weigh billions of tons on Earth. They have crushing gravity and often trillions of times stronger magnetic fields than Earth's. In fact, magnetars, a special class of neutron stars, boast the universe's strongest magnets and occasionally unleash giant bursts of X-rays and gamma rays. In short, a neutron star is a cosmic monster, and a close flyby would be a very big deal. What happens depends on how near it comes. Even at several astronomical units away, its gravity and radiation matter. For context, typical stars in our neighborhood sit a parsec approximately 3 light-years apart, so a passage near the sun is extremely rare. But suppose one did approach within, say, a few astronomical units. 1 astronomical unit equals Earth-Sun distance. At that range, a 1.4 solar mass neutron star would tug on Earth almost as strongly as the sun does. It could perturb planetary orbits or trigger tidal bulges in the oceans and crust. If it got really close, fractions of an astronomical unit, tidal forces could start to deform or even rip apart bodies. For Earth, skimming too near might cause massive earthquakes or volcanoes as the solid globe is stretched. The familiar spaghettification seen in extreme cases for objects near black holes. Gravity would also fling outer solar system material inward. We might see an intense comet shower. In fact, passing stars are known to shake up the distant Oort cloud, sending comets into the inner system for millions of years. A neutron star flyby would act the same way. Long after it leaves, our system could face a barrage of comets and asteroids. But the biggest danger comes from ionizing radiation. Many neutron stars are pulsars or magnetars, beaming X-rays and gamma rays along their magnetic poles. If Earth found itself in the path of those beams, we'd be bathed in extremely high-energy light. Models show that a powerful burst lasting seconds to minutes would ionize and dissociate atmospheric molecules, creating enormous amounts of nitrogen oxides. These compounds catalyze the destruction of ozone. In one study, a typical galactic gamma ray burst delivered to Earth's atmosphere, as might happen if a nearby magnetar flared, was found to produce approximately 10 times the normal nitrogen oxides and destroy 35 to 40% of the ozone layer globally. In fact, models predict up to approximately 3 times the usual UVB reaching Earth, enough to cause massive DNA damage to life. The gamma or X-ray blast also makes the air itself darker. The new nitrogen oxides would coat the stratosphere like an orange haze. That dimming could briefly chill the planet, possibly triggering or enhancing a glacial period. There's also the immediate blast of radiation itself, a direct hit by a giant magnetar flare. In 2004, a magnetar just 50,000 light-years away shone so brightly in gamma rays that it briefly altered Earth's upper atmosphere, boosting ionization by factors of 100 to 1,000 near 30 to 60 kilometers altitude. Ours is far closer, so the effect would be vastly stronger. So, a passing neutron star could threaten us in many ways: gravitational chaos, cosmic debris showers, and most disastrously, global radiation and ozone loss. However, it's worth noting just how unlikely this is. Neutron stars are rare, a few per million stars, and even weirder, those close enough to affect us are vanishingly few. Astronomers do model these scenarios to understand past extinctions on Earth. For now, though, the biggest threat to our ozone is us, not an exotic dead star.